Sparse signal deconvolution. Sparse deconvolution finds variety of application and accurate estimation of multipath channels with sparse impulse response of a channel is calculated by degradation version of convolution matrix. After down conversion to baseband, the signal from all the satellites can be represented in complex baseband representation as, where alpha, s, is the channel attenuation from the SDH satellite to the receiver, tau is the time delay or code phase of the CA code, and Fd is the Doppler frequency for the SDH satellite. We assume that the observed GPS signal Y from a multipath channel can be written as, where X is the signal of interest which is to be estimated, N is additive noise, and H is a matrix representing the degradation process. The estimation of actual GPS signal X from the faded version Y can be treated as a linear inverse problem. An appropriate objective function, Jx, has been formulated to solve linear inverse problems and to find the signal x, by minimizing Jx. Generally, the chosen objective function is the sum of two terms, where dy, hx, measures the discrepancy between y and x. Our x regularization term, or penalty function. Lambda regularization parameter, positive value. To find a signal x, so that hx is very similar to y, i.e., here it is needed to find a signal x which is consistent with the observed data y. For dy, hx, the mean square error can be calculated as, the squared error between y and hx is minimized by finding the norm difference of dy, hx, that will give a signal x, which is as consistent with y as possible, according to the square error criterion. To minimize dy, hx, by setting x equals h minus 1 year, however, h may not be invertible. Let convolution filter be, 1, minus 1, 1, minus 1, m, and signal be of length m. Convolution sum will have length equal to n plus m1. So h in this case will have n times m1 dimension, which is definitely invertible. Even if h were invertible, it may be very ill-conditioned, in which case, this solution amplifies the noise, sometimes to such an extent that the solution is useless. The role of the regularization term Rx is exactly to address this problem. The regularizer Rx should be chosen so as to penalize the undesirable/unwanted behavior in X. By assuming that the GPS signal of interest after acquisition X, is known to be sparse, i.e., X has relatively few non-zero values, i.e., X consists of a few impulses and is otherwise zero. In this case, the Rx may be defined to be the number of non-zero values of X. Rx is not a convex function of X, which is not differentiable, then the objective function Jx is very difficult to minimize and therefore Jx will have many local minima. To minimize Jx, it is better to choose Jx to be a convex function of X that measures sparsity, but which is also convex. For this reason, when X is known to be sparse, the regularization function Rx is often chosen to be the L1 norm. Hence, the approach is to estimate X from Y by minimizing the objective function. The requirement for development of fast algorithm is to minimize the equation and its related functions. This is carried out by another significant algorithm called iterated soft thresholding algorithm, ISTA, also referred as thresholded Landweber, TL, algorithm. ISTA is a combination of the Landweber algorithm and soft thresholding. To minimize Jx, consider first the minimization of the simpler objective function. Because Jxn, 8, is differentiable and convex, thus one can obtain its minimizer by setting the derivative with respect to x to 0. The derivative of Jx is given by setting the derivative to 0 gives a system of linear equations. So the minimizer of Jxn, 9, is given by. However, it is not able to solve these equations easily. Since GPS data is a very long, then H will be very large matrix and solving the system of equations may require huge memory and computation time. Moreover, the matrix height H is not invertible, or ill-conditioned. By using the majorization minimization, approach to minimize Jxn, 10, solving a system of linear equations can be avoided. At each iteration k of the approach, a function gkx that coincides with jx at xk has been found. A majorizer gkx has introduced that can be minimized more easily without solving a system of eks. a function gkx that majorizes jx by adding a non-negative function to jx. When gkx coincides with jx at x equals xk, the non-negative function added to jx should be equal to 0 at xk, then gkx to be. The function which is added to jx is clearly 0 at xk, so that gkx equals to jxk as required. To ensure the function added to jx is non-negative, for all x, the scalar parameter alpha must be chosen to be equal to or greater than the maximum eigenvalue of hth, i.e., alpha greater than or equal to max eig, hth. Then the matrix alpha I hth is a positive semi-definite matrix, meaning that Vt, alpha I hth, V greater than or equal to 0. Now, using procedure, to obtain xk plus 1, function gkx is minimized. Expanding gkx in 12 gives. Note that the quadratic term in 12 is simply xtx instead of xththx. Therefore, we can minimize gkx more easily. Hence, by using procedure to obtain x value at each iteration is given by Landweber update equation as